Swayam Prabha. Digital India. Educated India.
So this is your Spark program. Okay. So this is how you implement MapReduce with Spark. Okay. So this is just to show that Spark is actually a more general framework than MapReduce. Okay. So you can just create a MapReduce program by running flat map and then reduce by key and then map. Okay. Or group by key and then map. So here my map func is the mapper function and my reduce func is the reducer function. Okay. Yeah. So what will you do for word count? How will you do word count in Spark?
Write these two functions. Mapping table, give all the words, create all the key values.
Right. Yeah. So you can just do a flat map. Okay. Flat map and the flat map would generate just the key. Okay. Value is by default 1 for everything, and then you do reduce by key as the add. Okay. So that is a simple way of doing word count. Okay. So the difference between map and flat map in Spark, map creates only one output record per input record, whereas flat map can create multiple output records per input record, just like the MapReduce map function. Okay. So the map function in MapReduce is actually a flat map function in Spark. Okay. So how will you do matrix multiplication? Suppose you want to do a matrix multiplication, what should be the logic? So matrix multiplication will have two input matrices, right? Two huge matrices. How will the matrices be stored in a distributed manner? So one simple way of storing matrices in a distributed manner is each record, you have one record for each entry in the matrix. Okay. So the matrix has a row index. Every record in the matrix has a row index, a column index, and the data. Okay. So how many records are there then for this matrix? The number of entries in the matrix, and the record is of the form row index, column index, data. Okay. So this is a 3 tuple which is your record. Okay. Now there are two matrices, let's say A and B. So which transformation do you have to use in order to do the matrix multiplication? So what must happen for the matrix multiplication to function? Okay. So you see the column indices. So for the first matrix, so let's say A is the first matrix. Okay. So in the output RDD, okay. So there are two RDDs, A and B. Okay. So in the output RDD, for every row index of A, there should be one. There should be, so every row index should go to a different record, right? Because every row of the input, the first input matrix, okay, creates a separate record in the output matrix. Clear? Okay. But the columns should all go to the same one. Okay. And for the second matrix, every row should go to the corresponding column of the first input matrix, right? A matrix. Okay. So your key for the first matrix should be, your key should be the row index of the first input matrix and the column index of the second input matrix. Okay. So, okay. And for each of these, the value should be either the column index of the first input matrix or the row index of the second input matrix. Okay. And these should, and then you should group by key. Okay. So, then these, all of them, they go to the same record. So, you will have a record which will have entries of all the, a particular row of the first matrix and the entries of all the columns of that matrix, and they will go together. Okay. And then you multiply them and you add them. Okay. So, and this way you can create RDD which contains the row and the value for the output matrix. Okay. So, and okay. What should be the key here? So, you are trying to compute A times B, right? And which entry of this you should compute? I comma L, right? You should compute the ILth entry. So, the key here is I, the key here is L. Okay. Now, what should be the value here? So, the value should be J comma you already have the key as I, sorry, so let me make it I, okay. And if it is a second matrix, your value should be K comma okay. So, what should show, so when you group by key, okay, you will get, what will you get? So, for every I comma L, you will get a big list. What will this list contain? This list will contain, so 1 comma AI1, 2 comma AI2, and let's say your inner dimension should match. So, let's say the inner dimension is 10, this will have 10 comma AI10. Clear? Okay. And it will also have your 1 comma B1L, 2 comma B2L, 10 comma B10L. Okay. So, once you do group by key, so once you have this I and L as the key and these as the value, and you group by, you do group by key, each record that you get will be of this form. Okay. And you have to process this. Okay. So, then you have to do a map Okay, so you have to do a group by key, and then you have to do a map which takes this, matches this to this, multiplies these two, okay, and then adds them up, and then outputs that. So summation over A I A B A L. Okay. So this should be computed by the map function that you provide. Is this clear?
So we have to write code for doing what? As in, I'm just like,
So what should your code look like, right? So can I say new here? Very good. So what should your code look like? Your code should look like something like this, that you have to have, let's say there is a, so there is also something called union, by the way. Okay, so if you do union of RDDs, it just puts the records together. So you can take the RDD A union B. Okay, actually the statement, Scala statement will be something like A dot union B. So this will be an RDD. Okay, dot you will have to do a map which takes the appropriate key, which is the first one, right? So okay, so if you see the first key, so this has to be this function. So it will take the key and the value. Then you have to do a group by key. This will create the second RDD that I just mentioned, and then you just have to create a map where you have to implement the aggregation function, and then you are done. So you have a new RDD which have,
so this was a very simple program like matrix multiplication. If we have huge programs that we want to execute it through macros, so
not MapReduce, Spark.
this part, yeah. So we'll have to change each and every operation. Assume it is written in Python. Will we have to
Nothing, you just have to provide the function here, right? So you will have to do, let's say, def M1, okay, and then whatever it is, okay, and then so here is X, you do whatever processing you write, huh? You do another def M2 X, you write whatever you write, okay, you just write here M1, you write here M2, that's all. So you have to define these functions, and you have to so it is like, so this matrix multiplication will be something like 30 lines. So now you think how complex a program you can write. Okay, so let us go look at some more programs. Okay, so logistic regression. So all of you know logistic regression. Okay, it has been taught already. I will. So how will you design a Spark program that does logistic regression? So what should be your input RDD? What should be the record of input RDD? X, Y values, okay. So for each data point, each record should correspond to one data point, and it should have the X, Y values, okay. So your X in this case is the RDD, and so what more do you need? You need the W, right? So you need the parameter for the logistic regression, and that is nothing but just a local variable. Okay. Your data set is huge, but your parameter is not, right? So your data set is distributed in the memory in multiple computers, and then this is just one line. So you have a function which, given the parameter w and the data point a, which has both x and y components, okay, it can compute the gradient. Gradient is a vector of size. What is the size of the gradient? Number of parameters, same as w. So it creates a vector, that is the mapper. Then you just add the gradients over all the data point, okay, using the reduce function, okay, you get the gradient, okay, and then you just take a step. So taking the step, is it, so forget the line search, line you can just use some fixed step size if you want, okay, and then the last step, this step, the w is equal to w minus step size into g, okay, this is your update step. So where is this update step happening? Yes, but in which computer is this happening? It is happening in the driver program, okay. So this update step is not, it doesn't even use a single Scala construct, a Spark construct, okay. So it is just a Scala program, okay. So Spark is only storing the data points, and using map and reduce you are computing the gradient in a distributed manner. Once you compute the gradient in a distributed manner, it comes to your driver program, okay, and then your driver program is just updating the weights. This is a local operation in the driver program, okay, and you can do this many times, okay. This is one way of implementing gradient descent, okay, which you will probably be doing today, okay. And then you can see that you can run it on many cores, like you can run it on 6 cores, and you can run it on 30 nodes, and then you sort of you get some sort of a scale up, okay. So as you, for the same data set, you can increase the number of nodes and see how much faster program is running, and this is what I have plotted here, okay. Is this clear, the graph? So x-axis is the number of nodes and y-axis is the amount of time. So as you increase the number of nodes, it should, so initially it is a linear speed up, and then it sort of becomes saturated, because there are too few data points and too many computers that you are using, okay. So then the communication takes more time and overhead is more than actual speed up. CG is conjugate gradient. So you know, it maintains an estimate of the Hessian. Actually, second part we will not discuss conjugate gradient, but we might discuss some things, okay. So any questions about this? Okay. Okay. How will you do page rank? So all of you know page rank? Okay. So how will you do page rank in Spark? The adjacency matrix, yes. Okay. So one RDD is the adjacency matrix. Anything else you need? So adjacency matrix means what is the node? So adjacency matrix means you are looking at some graph. So what is the node in the graph? So the node is URL, right? Okay. And adjacency matrix stores which URL points a link to which other URL, right? So that is one thing. And so let me see. So just a reminder of the algorithm. So the algorithm basically takes, so it has something called a rank, right? So what is the rank? Rank is nothing but the score of a particular URL. So you basically have two things. You have the adjacency matrix, okay, and you have the score or the page rank score of each URL. So always the key of your RDD is the URL, okay. So URL is the key, okay. In one case you have the keys that link to this particular URL, okay, which is the adjacency matrix, that is RDD1, okay, which is also called the links RDD. The other one is the ranks RDD. So let us go. So this is the running. I will skip over the running because you know all these things. So there is the links RDD and there is the ranks RDD. Okay, so links RDD is basically storing the neighbors, okay, and rank is storing the rank. So ranks RDD is, links RDD is given to you and ranks RDD is initialized to 0 or something, okay. And then what you have to compute is the contributions of the neighbors towards the rank of the current neighbor, right? So you have to join these links with ranks, okay, based on the URL. And then for so you will get something like this. You will get the URL, the neighbor, and the rank, okay. And for each of these neighbors, okay, there will be a list of neighbors, of course. So for each of these neighbors, you will have like the destination and the score, basically the contribution. So the current rank in the current iteration by the neighbor size. Okay, this is the URL algorithm. Okay, and this is your new output key. So this destination comma this contribution goes to whichever is this so destination, right? So it goes to that URL. Okay, so you reduce, then you use reduce by key to compute the revised ranks RDD, and then you add 0.5, 0.15, which is like the your restart factor, right? So random walk with restart, and you keep running this over and over. Is this clear? Okay. So you will run, so you can run alternating least square. I will not go into this. What I will quickly do, so I think you have, so one crucial concept I will discuss is this scheduler. So how does everything really work? Okay. So I told you that there is this lineage graph that is constructed when you define the program, okay, and then what happens, okay. So then what happens is you have a graph like this. So this is a lineage graph, okay. So now, so what are the nodes in this graph? What are the nodes in this graph? The RDDs that you have created, right? The RDDs that you have written your programs one after the other, so you have created many RDDs, okay. So every RDD that you have created is a node in this lineage graph, right? Yes? Okay. And every RDD has been created from either some other RDDs or from a text file or a parallelize command, right? Okay. There is no other way of creating an RDD. Okay. So what are these kind of links between these RDDs? So you see there are two kinds of links, right? One where there is a lot of crisscross, another where there is just straight line. Can you tell what are these straight line things? One to one, right? So for example is Example is map or union, where one record, so these are so first of all you have to understand that these links between nodes have to be transformations, okay, because that is how one RDD is created from another RDD and another or two, even two. So for example, this is a join operation, so this RDD G is created from two RDDs B and F, okay. But again, then this is an union operation, it takes as input two RDDs, whereas something like map or group by key or reduce by key, it takes only one RDD, okay. So either it's like there is an edge from one RDD to another and there is only one edge, or there is two, okay, something like this in this graph. Moreover, there are these what is called a fat dependency and a narrow dependency, either one in one dependency like map or like group by key, which is called a fat dependency, okay. So if there is a fat dependency, then you put what is called a stage boundary. So the moment you see there are two stages, so the whole execution gets, if you have when you execute Spark program, you will see stage 1 executed, stage 2 executed, stage 3 executed, and then the job is over, okay. So the task is split into stages, and this is how stages are decided, okay. So stages are where the fat boundaries. Now until and unless a stage, the previous stage finish executing, the next stage cannot start. So this RDD B will not be materialized until stage 1 happens. But this RDD D can be materialized even though this map operation is not over. Why? Because there is a 1-to-1. So you can immediately, the moment one record of this D is created, you can start utilizing that record, because you know that this record depends only on one record of the previous RDD. But you cannot say that for, let's say, something like the B. So one record may be created, but then there may be something more added later, because another mapper, another task is executed. So here there is no mapper, there is only task, okay. And then this is how the Spark scheduler works. So it breaks down the program into stages, and then it executes the stages one after the other, okay. I will skip this. There are many optimizations that you can do. You can do something called co-partitioning, where you can do caching and you can do co-partitioning. These are two ways of making your Spark programs much faster, okay. Yeah, I will just, and you get the physical execution plan. And okay, so I will stop here. I don't have time to go into Hadoop system, so I will stop here. Any questions on this part?
We are doing materialization on D. What is the meaning of materialization?
Materialize means, see, one thing is you create the graph, okay. The graph means only that diagram. Think of it like some representation of that diagram, okay. So that size of that is like a few hundred or few thousand bytes, okay. But when you do materialization, you have to also compute all those things, okay. That each node in that graph may be like a gigabyte or something like this, distributed across the memory. So when you run the Spark program, which you will do today in the afternoon, you will see that when you define the computation, until and unless you define an action, okay, everything it will show very fast. It will show that the computation is done, but nothing is done actually. All it has done is created that graph. Okay, that graph is very small, so it is done very fast. Now when you give the action, okay, it then starts executing. So that is the materialization. That is when the real computation happens. And for real computation to happen, this scheduling, task scheduling, everything has to happen at that time. Until that time, nothing needs to be done. Okay, you need to know where each and every, so you saw this graph, right? So the starting of this graph is some file. That file is there on some machine, okay? So your first task has to be scheduled on that machine. Otherwise, you have to unnecessarily copy the data over network. So that has to be minimized. Okay. So then the Spark execution engine would ask for an executor on that machine. Okay, and it will schedule that task there. Then it will wait for that task to complete. Okay, like that, it will create the entire execution plan or execution schedule based on the stages, and then it will execute like that. So that whole thing is called materialization. Any other questions?